Sure.
Hello, everyone. Welcome to our seminar series on games, decisions, and networks. Today, our speaker is Professor Asuman Ozdaglar. She is the MathWorks Professor of Electrical Engineering and Computer Science at MIT. She is also the Department Head of EECS and Deputy Dean of the Academics in the Schwarzman College of Computing. Her research expertise includes optimization theory with emphasis on nonlinear programming and convex analysis, game theory with applications in communication, social, and economic networks, distributed optimization and control, network analysis with special emphasis on contagious processes, systemic risk, and dynamic control. She has received many awards, including a Microsoft Fellowship, the MIT Graduate Student Council Teaching Award, the NSF Career Award, the 2008 Donald P. Ackman Award of the American Automatic Control Council, the Class of 1943 Career Development Chair, the inaugural Stephen and Rini Innovation Fellowship, and the 2014 Spira Teaching Award. She served on the Board of Governors of the Control System Society in 2010. She was an associate editor for IEEE Transactions on Automatic Control. She was the inaugural area co-editor for Games, Information and Networks in the journal Operations Research. She is the co-author of the Convex Analysis and Optimization book published in Athena Scientific in 2003. And she is a wonderful supervisor. Francesca, Kaichin, Ozan, and I strongly agree on that. And thank you very much, Professor. We are delighted to host your talk.
Thank you very much for the kind introduction, and the last sentence was what made my day out of everything. So thanks so much for having me. It's a pleasure to be here and presenting this work. I'm actually very excited about this work. So this is joint work with Mohammed, who just introduced me, Francesca, Parise, Kaichin Zhang, brilliant researchers, all former or current postdocs at MIT now, in different places, as well as Tamer Bashar from UIUC and David Leslie. So what I'll talk about in this talk, I picked a fancy title to attract attention, but it's basically, we're going to be talking about multi-agent learning in stochastic games. It's a topic very dear to my heart. I worked on it in the past with limited success. So recently we were able to get some results thanks to Mohammed, Francesca, Kaichin's leadership on thinking about designing and analyzing very reasonable learning dynamics, simple and intuitive learning dynamics, convergent learning dynamics in stochastic games. So I wanted to share that with you, with the hopes that this will sort of motivate more research and more progress in this important area. So just to set the stage a little bit, and this is sort of how I view, like I got excited in this because really to be able to make progress in this area, you put together ideas from reinforcement learning literature as well as game theory, learning in games literature. So reinforcement learning clearly, where we think about an autonomous agent who needs to maximize payoffs or rewards in an uncertain dynamic environment, has emerged as the backbone of many AI problems with promise in several applications. And I hope you will agree with me that if you think about many AI systems, these involve multi-agent settings. So this ranges from the most popular these days of games, playing games literature such as Go or other video games, or thinking about robot grasping via multiple connected robot arms. A lot of people are thinking about human robot interaction or with control with human in the loop. Many are interested in autonomous vehicle control in dynamic traffic, intelligent transportation systems, or similarly, automated intelligent warehouses, production facilities, or control of UAVs. So you can see that all of these involve multiple agents. So really, in my view, further advances critically depend on thinking about dynamics or learning in multi-agent environments. And if you think about sort of RL and the main mathematical framework it builds on, which is the theory of MDPs, it basically assumes an agent's environment is stationary. It doesn't contain these adaptive other agents. So it's not really appropriate for thinking about learning with multiple agents. And of course, when you look at Game theory, learning with multiple agents, has a long history in game theory, probably as long as the discipline itself. And a very appealing, popular approach in terms of learning dynamics is fictitious play, whereby it's a best response type learning dynamics. The assumption is that you have myopic players, myopic in the sense they don't take into account the impact of their action on future actions or payoffs. So what they do is they observe the play, they play and observe the play, and form an estimate of their opponent's strategy using the empirical distribution of past play and play just the best response to that. So this is something introduced by Robinson, analyzed by lots of different people, lots of variations. Ozan also loves this method and has done a lot of work on this. But despite the importance of many of these issues, really, if you think about dynamic environments, there's limited progress. And the main challenge is really when you have many adaptive agents adapting their behavior and, in the presence of dynamics of the environment, it leads to a non-stationary environment, making dynamics or learning rules difficult to sort of have nice behavior. And if you think about more natural RL setting where we don't even have a model of the environment. So this is what we'll be referring to as the model-free case. And that's when we don't know transition properties, we don't have an MDP to model the underlying dynamic environment. And even when the payoff functions are unknown in some cases, these challenges are further amplified. And even though I think even in the model-based case, I'll try to make the case that there are limited results. So I wanted to put sort of a perspective on the literature. There's a lot of literature on these things, beautiful literature. So let's maybe start with classical results. And most of this is for zero-sum games. So of course, a seminal paper in this space is Shapley's 53 paper, where he defined the model of stochastic games. And this is very nicely described actually in a way that sort of it extends strategic form games, which is attributed to von Neumann from 50s to dynamic environments, and also extends entities, which is again developed by researchers in the Rand Institute, again in 49-50 framework to competitive situations with more than one decision maker. So it seems like these 50s is a very productive time, for these multi-agent dynamic interactions. And when you look at Shapley's paper, basically what he analyzed is a value iteration type algorithm using minimax operator to compute the value function in zero-sum stochastic games. So min-max, fixed point of min-max operator in zero-sum games is what gives us the equilibrium. So just iterate on it, just like we do in using the DP operator, using value iteration type algorithm, where you do all the updates simultaneously over all states. So this is great. I view that as an algorithm. And you can look at then another very interesting paper, which is quite, I guess, later, but I view also as seminal to sort of think about the same question in the context of model-free environments. So then, instead of doing value iteration, what this algorithm considers is a Q-learning type dynamics or algorithm, where updates are asynchronous, and essentially you update without knowing the underlying transition probabilities. And Littman introduced the algorithm. There's analysis by Littman, Sapeshvari. This is for zero-sum games and similar ideas. Once you get the idea, sort of how do you do it for non-zero-sum? Well, you just put some fixed point equilibrium operator in between the equations, and there pops something on non-zero-sum. It doesn't converge, but it's an algorithm, and other types of algorithms that were considered. So I think the point I'm trying to make is, these are generally computational in nature, sort of relies on very much the min-max operator and being able to iterate and its contraction properties. So if you look at more recent literature on multi-agent dynamic learning, there are really two strands. And one is more thinking about centralized case or coordinated case, however you want to call it, optimization case. This assumes existence of a centralized controller that basically can simulate and jointly learn all policies for all players. And there's a number of papers here. I think the one that we are interested in is this so-called decentralized or independent learning, where agents are, strategic, act in their own interests, and behave myopically and optimize their policy given their observations and beliefs. So this might be for various reasons. It might be because you have a very large system, a centralized simulator is not possible. So you let, you have agents with local information, you let them basically do whatever is best for them. Or, which would be the case, for instance, in a traffic scenario, or I don't know, maybe you have a lot of robots going around doing stuff with local information, or you really have agents that are self-interested. So you're thinking about a human and several machines interacting, each of them with their own objectives. So I think, so this is sort of where, game theoretic interactions are much more prominent. Okay, so limited results in this space, and there are beautiful papers that actually shows that there are fundamental difficulties when you're thinking about this independent learning, as I mentioned, because of the non-stationarity of the learning environment. So this paper in particular shows that even with when you have perfect oracle access to the game, which basically computes the Q function values for every opponent's strategy, weird phenomena may happen for naive learning approaches. They may cycle and fail to converge to an equilibrium. There are a couple of other papers, and I actually don't know how widely known. Borkar has a beautiful paper on this, thinking about an actor-critic type algorithm, thinking about weaker notions of equilibrium and showing convergence for these general cases. But again, it's a very, policy gradient, actor-critic type, again, I would say algorithmic flavor. And similarly, recently, there's some, I think, motivated by min-max progress, literature in the min-max algorithm progress. There are some distributed algorithms based on OGDA type methods, optimistic gradient descent ascent, that actually got some convergence results. So this is sort of the landscape to my knowledge, and there may be other papers. There's a lot of papers in this area. Mohammed knows. So two that I want to highlight, which are sort of super interesting, and probably what got us thinking in this space, is both from 2020, and very interestingly, one is from, it's a NeurIPS paper, I think, and this is GB, was it, Mohammed? So one is from a game theory literature, one is from a more
Journal of Economic Theory.
JET paper. So in Daskalakis, what they considered is, again, for zero-sum stochastic games, policy gradient type methods, but assuming that there is a 2x scale coordination between agent learning rates. So one goes slow, one goes fast. So it's not fully independent, right? The two agents have to coordinate to be able to achieve such dynamics. And this other paper, Leslie, is similar in terms of its consideration of this, multiple time scales, but at a different level. It considers the continuous time best response dynamics and calls the single continuation payoff common among all players, updated at a slower speed. So again, this idea of 2x scale, but again, with some coordination between the players. So that sort of motivates, I think, the question of, can fully decentralized independent dynamics probably converge for general zero-sum stochastic games? So that's what we do in these two papers. We develop simple learning rules, and I would like to emphasize simple. These are best response type, rational, incentive compatible, however you want to call it. Rational is used with many different meanings, so let me not use that. Simple learning rules which make sense from the player's perspective, guarantee convergence in multi-agent setups. Crucially, this is the simple and reasonable piece. They are fictitious play type dynamics, and they do not require coordination between agents. They are fully decentralized. And the main idea is actually similar to these two papers. We do some 2x scale learning, but at the level of an individual agent. So we don't coordinate across agents. And how do we do that? Well, each agent, in the most simplest setting, I will consider multiple different settings and talk about, how to use these ideas in more and more minimal information environments. But in the sort of baseline setting, each agent is simultaneously estimating two things: empirical, or some estimate of the other player's strategy. And just like in fictitious play, we do this to an empirical distribution. But he also estimates his own continuation payoff. Okay, so two things, which makes perfect sense, because if he has an estimate of these two things, he can actually maximize and find a good action for himself at this period. I think maybe the crux of this paper, and I will talk about a lot of technical things, but if you don't listen to anything, just this is the part I want you to get. So there is a 2x scale assumption we're going to make, in that empirical distributions, my estimate of opponent strategies, are updated more frequently than the estimate of the payoff function. And this is also, I think, nice, because it's very consistent with the literature on evolutionary game theory. Now I will come to that in a second. I mean, essentially the idea is you update actions faster than preferences or payoffs. Okay, so that's sort of the intuition in terms of, or how you can justify this, 2x scale update dynamics. And then we're gonna then, once we sort of set up these conceptual ideas, we're gonna prove convergence using many things, but I think very cool techniques, from differential inclusion approximation, stochastic approximation, as well as some novel constructions of Lyapunov functions. And I will try to also get into these tools a little bit, because I feel like, this novel use of these tools is what also made it possible to get the results. And the hope is that we'll be able to use these in more general settings. In particular, this novel construction of Lyapunov functions, Mohammed has become a sort of expert in being able to construct very interesting Lyapunov functions. So I'd like to share that with you. Okay, so this is the setup. These are the ideas, and we will prove convergence for zero-sum stochastic games in 3 different settings. Baseline is, full information, model-based. So players know their payoff functions, they know they know the underlying transition probabilities, and they observe opponent actions. Okay, so that's the model-based case. Then we go to the model-free case. And I mean, I also like this showing these 2 cases, because just to show you, if you get one, going to the next one under some standard assumptions is pretty straightforward. So, I mean, we can go into the details in a second, but I think the model base is important to get. In the model-free case, we assume players don't know payoff functions, don't know transition probabilities. They just observe their realized rewards. And then final one is the minimal information setting. And this is one where, you do not observe opponent actions. There may be several cases where you do not observe the actions of other players, but you just observe your own payoff, your own state, and that you try to estimate something about, the Q functions, continuation functions, or indirectly the opponent's strategy in that case. So we'll see how sort of some of the ideas from the first 2 cases can be used in the third case to form indirect estimates of the opponent's strategy. Sorry. Okay, so that's the roadmap, and I will go into some math now. Sort of how do we set up the problem? So what is a stochastic game? Well, it's basically, think about an underlying Markov decision process with multiple players. So you have multiple states. We assume there are finitely many states S. And so at each state, both of the players take action. Okay, 2 players, Mohammed and Francesca, they take A1 and A2. And these are the sets of actions that are available to each. And this is the usual notation. Delta of AI is the randomization over all those possible actions. And then, of course, you take actions at this particular state. Actions are A1, A2. Each player gets a payoff, which we refer to as RSI. And then the joint actions taken by the players not only determine the rewards or payoff at that stage, but also it determines the transition probability. They control, so the transition probabilities are controlled not by a single agent's action, but 2 agents' actions. So that's sort of the differences, from a usual MDP setting if you're thinking about a stochastic game. Okay, and that's it. And now we're going to think about the discounted setting. So gamma is our discount factor. Okay, so actions at each state, multiple actions, as well as those actions determine payoffs and the transition probabilities. Beautiful. And then we focus on stationary Markov strategies, I guess, which exist in this case. So we're doing that without loss of generality. So essentially, the strategies I'm going to define will be just a mixed strategy for each possible state. And this is some notation. The notation for these, RL type problems are messy, but I'll try to do my best to clarify as much as possible. So for each player I, the strategy is a set of strategies for each state S. And of course, we said it's a random mixed strategy. Pi SI essentially is a mixing over AI at that state. Okay, so you take all the strategies at every state for each player, you put them together, and that's your pi, which is the strategy profile. And then we now can define the expected payoff or the value function of player I as just, you start from some initial state S, you run, this Markov process, which is this SK, that's the stochastic process. And then you assume that AK, the action at each stage K, is drawn from this strategy profile pi SK. Then you compute the payoffs at that AK for each player I. You discount it properly, and then you add it from K from 0 to infinity. Okay, so that's the payoff function at assuming you start from S, and then you take the expectation over initial distributions to get the payoff function. Okay, so that's how we define a payoff for a player in this dynamic setting. What's a Nash equilibrium? Well, hopefully, if you get this notation, it's easier to define. So a pair of strategies is a Nash equilibrium, provided that the payoff that player I gets under that is better or higher than anything he would get if he deviates while the other guy is fixed at the other strategy. And this value of Vi pi star is the equilibrium value function of player I. Okay, so that's our Nash equilibrium. It's a useless definition as this, so we need to find a way to characterize it. And the way we do that is basically we use dynamic programming, which is used to characterize the optimal in the single agent case, but we're going to do it for equilibrium values here. And the dynamic programming really relies on the Bellman's equation, which basically characterizes the equilibrium values at a particular state in terms of equilibrium values in successive states, and making sure that what you do at this stage is optimal, right? Okay, that's single agent. This is just a multi-agent version of that, also referred to as one-stage deviation principle. And what it is, okay, you fix the other guy, you look at your strategies, you deviate for one stage to from pi star I to some other pi I. That gives you, so your action is drawn from that, yet gives you some payoff, and then you stick with pi star thereafter. That thing is maximized at pi star. That's all that this is saying. So by deviating one stage, you cannot improve your equilibrium payoff. So that's the one stage deviation principle. This is, game theoretic characterization of or multi-agent generalization of the Bellman's equation. So the one thing that we need to think about especially because we're going to go into this model free settings, or actually in general, when we're thinking about sort of value iteration and one object that becomes mathematically convenient to analyze, but also makes it easy to simulate, is thinking about a Q function. And what is the Q function? So I always remember it only by swapping maximization and expectation. So that's what I was trying to sort of explain here. So we define now the Q function as this pink thing here, okay, inside this expectation. And then V pi star is then nothing but the maximum over pi I of the Q pi I star. We're keeping the other guy at pi star, and we're taking the maximum with respect to pi. So as you see, what we did by defining this Q function is instead of maximum of the expectation, we basically take the expectation and put the maximum inside. Okay, so that's the swapping of maximum and expectation, which makes it both easier to analyze and easier to simulate. So that will be our primitives. So what we will do for our dynamics is we're going to combine, basically, we're not going to do anything new. We're going to combine fictitious play with value function iteration in the model-based setting, and Q function iteration in the model-free setting. Value function is, I mean, I gave the reference of Ertzekas here, but of course, there's a large literature on that. What we're going to do is players will form belief on opponent strategies using empirical frequencies, and then also form beliefs on the equilibrium value function or the Q functions. And then players will choose the best response in an auxiliary game given their beliefs. And this is basically, I'm calling it an auxiliary game because I will replace the payoff, continuation payoffs by the estimates we have on the Q functions as well as, opponent strategies. So this is a trick that is also used in analyzing learning dynamics in repeated play of the same stage game. The issue here is that because these Q function estimates are also evolving, that sort of these auxiliary games are non-stationary. So it's different than analyzing learning dynamics for repeated play of static games. Also, that's just a side comment. Okay, so more specifically, and with some notation, this is just, shows the model-based case. We basically, at stage K, we're at some state Sk, and player one has a belief. One on his opponent's player two strategy, which we denote by pi2 hat, and then also on his own Q function, which is this Q1 hat. Okay, so once he has these two beliefs, he can act. So what does he do? He selects the best response. What is that best response? Well, it's just maximizing his expected payoff. To be able to compute his expected payoff, he needs the Q. This is, remember, it's a function of A1, A2. So he basically takes an expectation with respect to pi hat as well as A transpose, and then maximizes O rate. So this is, he forms his expected payoff given his beliefs and chooses the maximum action for himself, the best response for himself. And then once he gets this best response with respect to his beliefs, he updates these beliefs or estimates. So how does he update his belief on 2's strategy? Well, 2 does the same thing, right? AK2 is computed and he observes that AK2. So he gets that AK2 from stage K and then mixes it, just like a convex combination, the new information with his previous estimates. So this is the empirical distribution, right? This is how he's updating the empirical distribution of his opponent's play. And then he updates his belief on the Q function by basically, again, taking the Q hat, which was his previous estimate. But now he has a new estimate, which is current plus, the continuation payoff. And he can sort of compute that continuation payoff by maximizing, getting the best response with respect to the current beliefs at state S prime. So is this clear? I'm going a little too, I didn't say it very well, I think. So this Q hat is just, think about this as 1 minus beta here. So they say he's getting a convex combination just like before with the previous estimate and the new information. And the new information comes from basically thinking about at any action profile, an update on V hat, and that update on V hat is done using the estimates that he has about his payoff as well as the opponent's strategy. So this is sort of very standard assumption in lots of places. You just get the new information, but you get it slowly so that, you form an estimate with inertia using your previous estimate and the new information. Okay, so let's remember these blue things here. These are the learning rates. Alpha is the learning rate for the opponent's strategy. Beta is the learning rate on my own continuation payoff. Okay, so what does the model-free version look like? This will go like this from now on. I'll have the model-based, and one slide for model-free, pretty much. So if you don't know the transition probabilities or your own stage payoff function, you use something like Q-learning by Watkins and Dayan. And that's a stochastic version of what I just talked about. So if you don't know the transition probabilities, this is what we need, right? In this dynamics, this expectation. So you don't have these probabilities. So you estimate this expectation by the value of V hat at the next state, where this next state or the successor state is chosen with probability underlying transition probabilities of the Markov chain. So if you actually have a Markov environment and you're just following the transition, that basically gives you this V hat and makes this sample value an unbiased estimate of this sum. So that's the idea. You approximate the expectation by the realization of the underlying, realizations of the Markov chain. Is that clear? So this is sort of how this model-free case can work. So that's what we do here. We just change the way we update the Q function. Remember, this was the expectation. We just substitute here the V hat. Very good. And then the other difference is, of course, because now we don't have this information for all states, we're simulating, right? We're just going from SK to SK plus 1. This is just something we can do only at the current state action pair. So we replace this blue thing. We should have done this blue as well as a learning rate that depends on both SK as well as AK. So, and this is, of course, this is a counter, and that counter gets updated every time this pair SK-AK is visited, okay? And then we also have this additional assumption, which I always like, why do we do this? It's basically some exploration. We also make sure that, because in the analysis of these dynamics, for those who are familiar, you need some assumption about as long as every state action pair is visited infinitely often. So this is something that enables that, but also intuitively makes sense because it allows you to explore the underlying learning environment. Okay, so this is just some justification, I guess. Let me see how I'm doing with time. So a key feature was, again, I try to make sure we're doing estimates on two things, Q functions as well as opponent strategies. And we're going to do Q function updates, slower time scale than opponent strategies. And this is actually something you observe in evolutionary game theory literature quite a bit, that players' choices are more dynamic than changes in their preferences. So if we interpret Q functions as slowly evolving player preferences, right? This is the sort of non-stationarity, and Q functions are not fixed, but they're slowly evolving. So that's sort of what we would like to do. We would like to change Qs more slowly than we change our estimates on the opponent strategies. So this is what we would like to do. Mathematically, how do you achieve this 2x scale? Well, you just play with the learning rates. You make one faster than the other, okay? And that's the assumption we do here, pink assumption. But before that, I guess we need some standard assumptions, for making sure we can converge. So we assume each state is visited infinitely often. And this will hold as long as the underlying Markov chain is irreducible, right? So you can go from anywhere to anywhere. I don't know if that's very formal, but that's how I think about the underlying graph. And there's, where the links are induced by the probabilities, and that's like a connected graph. Okay, so that's a very standard assumption. And then you need an assumption on the learning rates. And the first one is, again, very standard for any such dynamics. You have the learning rates slowly going to 0. You make them infinitely summable, so you make enough progress. So these are very standard assumptions. The pink one is, I guess, the crux of our paper, if I may say, Mohammed. So we make sure that the ratio beta over alpha, if you look at that ratio as limit k goes to infinity, it goes to 0. So that's sort of saying that beta goes to 0 faster than alpha goes to 0. So you're making Q changes slower and slower while you're actually keeping the opponent beliefs, changes higher than how you would change the Q function values. Okay, so this is pink is important. And under these assumptions, one can show that the strategies converge to a Nash equilibrium for some stationary equilibrium, and then I guess the more interesting thing is the value estimates converge to the value of the game with probability 1. Okay, so and then for the model-free case, it's similar. Except that we need a little bit more assumptions, because as you see in the model-based case, we were updating at a particular state all of the possible actions. Q is a function of A. But in the model-free case, we can only do it at our current action profile, along the trajectory we follow. So that's why the model-free case is a little bit more errory. So it has more stochastic approximation errors that you need to control. So you do that by essentially first assuming that the primitive here is, remember I said state action profile. So they need to be infinitely often and frequently enough. Yes. Okay, let's say infinitely often. And then if you actually, this will hold. Remember the exploration probability that I mentioned, because you explore any action state pair, then this assumption holds. And then the learning rates assumption is, the usual assumption we had before, but we do now a little bit more assumptions, sort of more second order bounded variance type assumptions to be able to control the additional stochastic approximation errors that are introduced. And here, again, because your counter moves with SKAK, the going to zero assumption is replaced by this sort of more stronger assumption. And this part B will mean that this beta will have to go to zero faster than what you have in model-based case. And the paper has lots of different technical stuff under which this holds. So it gives many different beta and alpha steps like learning rate sequences that satisfy these kinds of assumptions. Okay, so I hope it's clear, like the difference between model-based and model-free. And then under those assumptions, you again get that, okay, this is a bit fishy, I guess, but anyway, when epsilon is zero, but then the assumption doesn't hold, so you need to make sure epsilon goes to zero a little slowly. So, but that's hard to write in one slide. So assume epsilon is zero, then you get convergence to equilibrium. And if you have epsilon positive, then you get approximate convergence to the value of the gate. Okay, so you can actually, if you're, if you say, also these are very restrictive assumptions, we can get less restrictive assumptions with a little bit more technical details. Okay, so
quick clarification question. So the beta and alpha parameters are identical across agents, correct?
Yes.
Is that an assumption that can be relaxed? Like for as long as the orders are the same and alpha is, sorry, one of them is of smaller order than the other one, agents do not necessarily have to have identical parameters? Would something like that hold true?
I will say yes, but I will defer to Mohammed.
Okay.
Yes, yeah. Indeed, this is an ongoing project, and simulations suggest that they converge. Yeah.
Perfect. Thank you.
Alex.
Hi, so both in this theorem and the previous result, you qualified for some stationary equilibrium. So it doesn't hold for all. Is there a reason?
It converges to some equilibrium. There could be multiple, and it converges to some.
So I see. Okay.
But the value is unique, right? So the value converges, and it converges to some equilibrium. Okay. Good. Good. So now I will go into a little bit of analysis, and this is sort of where I hesitate. Should I? So this is going to be a little bit technical detail, but I thought we should go over this because the tools, as I mentioned before, are powerful, but also enables to get a lot of mileage for the analysis. So I'll try to sort of show you how this blue assumption, this 2-time scale, is used and allows us to get results on convergence for such dynamics. So please stop me if any of the notation will be a little bit messy, but I hope the main ideas will be clear. So we'll basically, in the sort of this part of the talk, what we're going to do is analyze, for the model-based case, this sort of coupled dynamics. So we're updating these best responses, sorry, the opponent beliefs, and then we're also updating the beliefs on the Q function. Okay, this is what I wrote before. The issue is here, this coupling, because because of this pink thing, all of these stage games are coupled to each other. right? The continuation payoff really couples all of these different evolutions at all these states. So we're going to show that with beta over alpha going to 0, this coupling will be weakened. And essentially, to analyze that by removing this coupling, we're going to actually go into continuous time to be able to, show how things can be simplified. Okay, so how do I write this thing? Well, I write the second evolution in terms of, the alpha learning rate times some epsilon. And this epsilon is nothing but beta over alpha times the pink thing. Okay, so I've done nothing fancy here, just multiply, divide by alpha. And then because beta over alpha is going to 0, this epsilon is going to 0 almost surely. And therefore, you can think about this Q's. This is going to 0 to be, almost not changing. Remember, I was like this non-stationarity, this fact that these Q's change is the issue why we get into all these difficulties. So because of this assumption now, asymptotically, these Q's behave as they're not changing. Okay, so this removes the coupling, this removes the non-stationarity issues and allows us to get the analysis we're looking for. So, okay, how do I formalize what I just said very informally? We get the discrete time update, and then we use some continuous time approximation to be able to write things in continuous time. This is Benheim's beautiful work. Essentially, instead of this difference and the this sort of step size, we write it as pi dot is in. Again, this is the differential inclusion business because these best responses are not unique. In this argmax minus pi, and q dot is equal to 0. So that's epsilon going to 0. That's our approximation. We approximate it using stationary payoff function. Okay, and then you can go into I had a slide on this, which was impossible to read, so I removed. So if you use differential inclusion approximation theory, we can actually, it says that we can characterize the limit set of the discrete time update using this sort of differential inclusion, okay, the perturbed version of this differential inclusion, if we can find a Lyapunov function for this system. And what's a Lyapunov function? Well, it will have these properties, which is that along this trajectory x of t, it decreases. And whenever it's equal to 0, it remains at 0. And if we can find such a function, it shows that this v will go to 0. Okay? So then the first sort of crux of the proof is to find this is sort of one of the things I love most because it builds on a paper that I really like, Harris from '98, which analyzed fictitious play for static games, static zero-sum games. So we basically are now going to extend it to a stochastic game. And this is not a new slide. This is basically Harris's construction. And how much time do I have? I'm running out of time, but I will very quickly say. So Harris basically showed that the sort of best value of the best response summed over all players is a Lyapunov function for the continuous time best response dynamics in a zero-sum game. Okay, and to see this, you need to do very cute stuff like first this is non-negative, and let me maybe just show this one. It's non-negative in zero-sum games because if you take it for player 1, now maximum is clearly greater than the minimum by minimax inequality, and then you can rewrite this minimum as minus maximum minus, and minus QS1 is QS2 because it's zero-sum game. So if you put this maximum on this side, you will see that the two maximum sum of the two is non-negative. So that's the non-negativity. Oh, sorry. And then the other one is to show that basically d by dt is positive. And essentially, you do that by, this is the maximum, right? And you use envelope theorem as well as the evolution of pi around our along our dynamics to be able to show that v dot is something like minus v. I'm skipping details. This is really algebra, but it's important. This pink part is important. V dot is equal to minus v plus some a transpose q1 plus q2 a. And when the game is zero sum, this pink part is zero. Okay, and when that pink part is zero, this gives you basically that VH is decreasing. Right? Whenever VH is positive, this thing is negative, so it's decreasing. Okay, so but we saw that the role of the zero sum in this construction. So this needs to go to zero to be able to make that, this needs to be equal to zero to be able to make that argument. So the problem for stochastic games is that, yeah, in Harris, this condition plays a crucial role. Here, the problem is that even though the underlying stochastic game is zero sum, meaning at every state, R1 plus R2 is equal to zero. Remember, our primitives is continuation functions, Q1 and Q2. And everybody is forming estimates on those based on some stochastic stuff and plays and so on. So Q1 and Q2, when you add them, they're not zero sum. So this argument doesn't hold. They're not necessarily zero sum. So you need a new Lyapunov function to address the deviation from the zero sum structure. And basically, the idea is actually exposed may be very simple. So you again get Harris's Lyapunov function, right? But you want this part to be negative. So you want to make sure that no matter what A you pick here, that term is negative. So to be able to do that, you just subtract from it some lambda times the maximum norm of the sum of these two matrices. Okay, so that's sort of the trick that was used here. And you choose lambda in a, this is true for any lambda, but you choose lambda in a smart way so that some of the other steps hold true. Okay, so I'll maybe go quickly over now the final part of the convergence analysis. So we have a Lyapunov function now, which is the sum of the maximum like best response payoffs for the players minus this sort of error term that you're correcting for. And then you consider, V hat, this is V hat I, right? This was our, this is maximum over Q hat is our V hat. So you consider Q bar, which is the sum of these Q hats, and V bar to be the sum of these V hats. And since this thing is going to zero, what this says is that this is the sum of, this is V bar. V bar, if this whole thing is going to zero, then is sandwiched between minus lambda Q bar and lambda Q bar plus some epsilon, which goes to zero, okay? And then once you have this, you can study the evolution of the sum Q bar using, so the first part, which was very important, was the Stenheim's continuous time approximation. The second thing, which is, I think, very key in this analysis, is the paper by Sissiklis from '94. And that is basic, this is very messy looking, but let me try to sort of parse this together. So you have some vector process X, which is progressing according to this dynamics. So this is, by the way, super standard dynamics. Any, lots of optimization algorithms, gradient-based dynamics very much follow this, so it's useful to know. And it's very general. It's probably the most, especially because it's asynchronous, it's very, very applicable to lots of different scenarios or algorithms. So you have this X that evolves as X plus alpha times some new information minus X. Remember, this is how many of the dynamics or belief updates I was writing looked like this, plus some errors. These are the stochastic errors. So W here is a martingale difference sequence, and epsilon is something that goes to zero. And F, I always think about this as gradient, but F is basically bounded from below and above by this xk, okay? You have a step size that goes to zero with the standard assumptions. Then also assuming X is bounded, this iteration gives you that xk goes to zero. So let's maybe parse this a little bit. This is asynchronous because this is dependent on each entry is moving differently, right? That's the asynchronous part. It's something like a contraction. Assume now alpha n is 1 and get rid of all the messes, w epsilon, assume there are zeros. Then what this is because fn is something like gamma xk, basically this is just a, xk is less than or equal to gamma xk with some gamma less than 1. So this is a contraction. So no wonder it goes to zero. So the stochastic approximation piece of this is you have a contraction. If you add some square integrable martingale sequences as well as asymptotically negligible errors, results continues to hold. So I hope I was able to parse this. So it's very important results. And I think I strongly recommend reading this paper for those interested in this kind of analysis. So that's what this is doing. And we will use that to be able to say that our Q bar and V bar goes to 0. Okay, so how do we do that? I will skip it now because I'm running out of time. Essentially, you have that Q bar is evolving like this. And remember, because of the Lyapunov function going to 0, V bar was between lambda Q bar plus epsilon. And then essentially it says that, this part here, this green part, is nothing but between, Q bar and Q bar. And epsilon is asymptotically negligible. And lambda was, remember, we chose it between 1 and 1 over gamma. So this thing is indeed less than 1. So this is just the stochastic approximation result, which shows that Q bar goes to 0. And therefore, because Q bar sandwiches V bar also goes to 0. So now I'm almost done. Please bear with me for one more second. You can also do, I removed some more algebra to show that V hats actually do track the value of the game. So V hat minus value is going to 0. So now the only thing we do is actually argue that what our updates do is nothing but Shapley's iteration, but a stochastic version of it. So Shapley's iteration is something like this with the value function. It showed it's a contraction. So our Q function estimates were something like this, but I now replace it with val, and I put the rest of it in an error, which is epsilon here. This error is the difference between our iteration was in terms of V hat. So by writing this like this, I just made it in terms of the val and put the rest in terms of V hat minus value. So essentially, this shows that the difference between Shapley's iteration is exactly the stochastic. This is an asynchronous approximation of Shapley's iteration, and using Stiglitz's result, you get convergence to 0. Okay, I hope I didn't lose you. I love this proof, so that's why I want to go through the details. But once you have this, basically, model-free cases really follows very similarly. You have a little bit more error, which is now the error due to approximating these expectations. And that's another stochastic approximation term. You can show that it's a square integrable martingale difference sequence. Again, Stiglitz's result gives you that this converges to, in the model-free case. Okay, so that's the model-based and model-free case analysis. Some simulations, yes, they converge type of simulations. And then you go into this final case, and I have only a few minutes left, so I'll try to sort of, this is also, I thought, very cool. I don't know if Kai Ching is here, he can jump as well. So this is basically, remember, in the model-free case, we assume that agents do not know their reward function and transition probabilities. They still access their realized payoff as the current state. But on top of the previous assumption or the previous setting, we also assume that they do not observe opponents' actions. Therefore, unlike fictitious play, we can no longer form beliefs on opponents. And this is the case where, which may arise, right? You don't always observe the actions of the opponents. You just observe your own reward. So how can one think about, learning dynamics in this case? And this apparently also is called as radically uncoupled or payoff-based learning in the literature. So the cute idea here is players estimate, now it's still two things. One is related to this continuation payoffs, the Qs as before, okay? We're gonna see that it's related to that Q. But the other one is some local Q function. So you get the global Q function. You don't observe A minus I. You take expectation over it, and that's your local Q function. And the realization, I guess, here was that this local Q function, because it's taking an expectation with respect to opponent's mixed strategy, it carries information about opponent's strategy. Okay, so this is some estimate you can form, which indirectly informs you about the opponent's strategy. So that's one object you form estimates on. And then you also form estimates on now the value function, no longer Q function, because you don't observe actions anymore. So this is now, you can think about it as an estimate of the global Q function, and it has information about both your own strategy as well as opponent's strategy. So this sort of serves the purpose of the continuation payoff over which you were forming estimates on. Is that good, Mohammed? Like I'm looking at Mohammed. It took me some time to figure out what's going on here. So then once you get this sort of setup to be similar to before, you have some indirect estimate of the opponent strategy. You have an estimate on your own continuation payoff. You use a similar 2-time scale learning framework, and you can get a dynamics with favorable convergence properties. So of course, there are details and a lot of asynchronism in all these updates, because now you only update it for the current local action, and then you need to do something very actually clever, which we got from Leslie's previous paper on individual Q learning. So the idea is, we're doing local actions asynchronously, only for the current action you're playing. So to have them sort of act more or less synchronously, or balanced in terms of in expectation, you use adaptive learning rates. So you use larger step sizes for local actions taken less frequently, smaller steps for local actions taken more frequently, and that gives you this particular dynamic. So I won't go into the details because I'm really out of time. So you do some best response given your estimate of Q hat, and then you update your local Q function estimates using these adaptive learning rates. Remember, I said you have to adapt it based on how frequently certain actions are being used. And then you update your value function estimates as before, and you get a convergence guarantee here. Some error is there because we are now using smoothed best response with some temperature parameter. And there are ways of getting this to 0, which I don't want to get into. It will be, I don't know, the third time scale or something like that, which enables you to get the exact equilibrium. But convergence analysis is similar to before. I mean, it's even, I guess we're going to be, because we have unique best responses, we don't need differential inclusions anymore. It's ODEs and again, similar constructions. Okay, so let me conclude there. I am surprisingly on time. We presented simple and intuitive learning dynamics for zero-sum stochastic games. They are fully independent because, and the innovation is really what I kept mentioning, this 2-time scale learning with respect to estimates on your opponent and yourself, your own payoff. And we feel this is very reasonable, assumption in terms of having an intuitive learning dynamics. And right now, I think, as Mohammed mentioned, I'm super interested in, this is zero-sum. Can we use this framework for other classes of stochastic games? Of course, we only presented asymptotic guarantees. Is there any, results around non-asymptotic guarantees? And, what we tried to do here is various different information structures. So also thinking about maybe other applications and other information structures where these could be relevant. So with that, let me conclude.
Okay, thank you very much. Also, that was a great talk. I wish that was my job talk. I don't know. Yeah. There's a question from Amy, and I can just relay it.
Yes.
Do these techniques offer hope that we might be able to achieve convergence in the non-zero sum case, since the per state games deviate from the zero sum assumption? Like, Amy, would you like to elaborate?
Amy, you're asking the questions I was asking, Mohammed, but unfortunately not. I was actually thinking whether I'm confusing when I was presenting. The Lyapunov function construction goes beyond zero sum. That's true. So you can actually construct that for non-zero sum games. But as you see, we did quite a bit more in terms of showing Q hats converges to the value of the game. And there we use quite a bit the zero sum structure. So I'm hopeful for more classes of games than just zero sum, but that even turns out to be, not trivial. I think we will be able to show for more classes of games, but not for, I don't think for non-structured games.
There's one more question from.
I don't know, Mohammed and, Kaiching, Francesca, add on to this. I don't know. Would you agree?
I believe we need to develop new technical tools for every other class. There is no universal tool to solve everything in this case.
But
especially
that's the case for even static games.
Yep.
The Lyapunov functions you use for learning dynamics for different classes is the case. But I think this sort of thinking about 2-time scale learning would be very helpful, I think, for other classes as well.
Okay, there's one more question from Hak Zhang. How does this technique compare to regret minimization techniques for two-player zero-sum games like counterfactual regret minimization that can also find Nash equilibria? Like, would you like to elaborate further, Zhang? You can just unmute yourself and ask.
Well, I guess, thank you for the talk. This was wonderful. I was curious to see that these dynamics seem to be based on fictitious play. And I was curious if there are similar results for regret minimization based techniques, which also converge to zero-sum Nash equilibrium in two-player zero-sum games.
We haven't looked at that. I can't see you, Zhang. It's a very interesting question. Now, I don't know the literature on regret minimization and stochastic games. I don't think there's, we haven't looked possibly, but I think I couldn't construct from the top of my head the relation of the dynamics, but definitely worthwhile to look at. Mohammed, do you know anything on regret minimization for stochastic games?
Yeah, I am not aware of an existing work, but Ozan is raising his hand.
Ozan maybe has something to add.
No, I have a question, not an answer.
But just so that, yeah, I think it's very interesting. It would be very interesting to look at.
I can say something about that, I guess.
Yes.
Which is just that the maximization operators can sort of intuitively be replaced by something that's maybe learning, doing regret minimization. So I think there's a little bit just very new work on that in the last couple of years. One paper by Ian Cash comes to mind. So I think there's thoughts about trying to integrate the two ideas, but I think there's not much yet.
Yeah, very good. Thank you. Well, I couldn't see you, but thank you. Ozan.
So two questions. The first one is, if I recalled correctly, the benign framework allows the perturbations to be stochastic, which would, I guess, in this case mean that alpha over beta, for as long as, alpha and beta need not be fixed parameters, for as long as they're either expectation or, for as long as it goes to zero in some sense, the results would generalize, would be my intuition. Is that correct?
Yes.
So alpha and beta need not be fixed parameters. Their ratio should be going to zero. It can have perturbations along the way. That would be fine.
I think so. They're not fixed already. They're going to zero. Or do you mean like they're not necessarily
deterministic?
Yeah. I think so.
Okay.
Oh,
I guess.
So that you're still into when the alphas are different between different players.
Yeah, exactly. I mean, I think that's an assumption that could be relaxed in this case, as Mohammed also indicated earlier. The second thing is, if I recall correctly, we kept a two-player assumption throughout, right?
Yes.
We
use zero-sum.
Right. I'm guessing that it could be possible to generalize the results to multiplayer extensions of zero-sum. So like the polymatrix games, network game, payoffs a couple over edges, and zero-sum. I mean, some of the, I believe Yang may be also on the call right now. Some of the nice characterizations of zero-sum elegantly extend to that case. I would be real interested to see if the results on dynamics do extend as well.
Let's do it. Like it. Absolutely.
Thank you for a fantastic talk, also.
Thank you. Well, very good. Mohammed, thank you so much for having me. I started by saying I really like this work, so hopefully I was able to convey my enthusiasm on some of these new ideas. So I agree, there's quite a bit of work that can be done here, and I hope people will pick it up. Thank you. Thanks a lot. Thank you for having me. Bye, everyone. Bye.
Bye.